Yes, good evening students. Welcome back to my channel. So in the previous videos or in the previous our Zoom classes, we discussed up to question number 35 in our material, page number 106. And in this video, I am going to explain from question number 36 in page number 106. See, question number 36, page number 106. Read question number 36. Two bulbs consume same power when operated at 200 volts and 300 volts respectively. When these bulbs are connected in series across a DC source of 400 volt, then the ratio of power consumed across them is. Read the question again. Two bulbs consume same power when operated at 200 volt and 300 volt respectively. From P is equal to V square by R, that P is given same. So P constant. Therefore, we can write here V square by R is equal to constant, or V square is directly proportional to R. So therefore, R1 divided by R2 is equal to V1 divided by V2 whole square. So here V1 is given 200 and V2 is given 300 whole square. That is equal to 100 cancel, 2 square is 4, 3 square is 9. So R1 divided by R2, or ratio of the resistances. Ratio of the resistances is equal to 4:9. Now these two bulbs are connected in series. Two bulbs were connected in series. In series combination, current is same. In series combination, same current flows through both the bulbs. So therefore, again from P is equal to I square into R, P is equal to I square into R. Current same, it means, so P is directly proportional to R. Therefore, P1 divided by P2 is equal to R1 divided by R2, that is 4:9. So what is asking here? Ratio of power consumed across them when they are connected in series, that is 4/9, option 3. 4/9, option 3 is the right answer. Next, question number 37. In the circuit shown, the resistance small r is a variable resistance. If for small r is equal to small f into capital R, the heat generation in small r is maximum, then the value of small f is. So in 37 question, first we should draw the given circuit. Here it is capital R and here also capital R. This is small r, but it is variable. Small r is given f into small f into capital R. Heat generation in small r is maximum, then the value of small f is. We know that heat generation Q, we have three different formulas: I square RT, or V into IT, or V square by R into T. Now here in the parallel combination, so observe here this portion. In the parallel combination, V constant, parallel combination V constant. So therefore, I can take here Q is equal to V square by R into T formula, because parallel combination potential difference is constant. And here R, this can also be written as Q is inversely proportional to R. Q is inversely proportional to R. So therefore, to have to have maximum heat generation. To have maximum heat generation, R should be minimum. R should be minimum. So that F is equal to, check with the options based on elimination method. First option is given 1, second option is 1 by 2, third option is 3 divided by 4, fourth option is 1 by 4. So we should choose the least value out of the 4 options. So that is F should be small number, that is 1 by 4, that is option 4. Option 4. Next, question number 38. Question number 38. A current source drives a current in a coil of resistance capital R1 for a time small t. The same source drives current in another coil of resistance capital R2 for same time. If heat generated is same, find internal resistance of the source. Here, same source when connected with two different external resistances in same time, it will give same heat generation. It is heat generation. Q1 is given Q2, or that implies we can take I1 square R1 into T is equal to I2 square R2 into T. Out of 3, why we should take only I square RT formula? That is based on the given data. Currents, same source drives current in another coil of resistance R2 for same time. Time is mentioned in the question, resistances are given, and regarding the current also point is there in the question. That's why we should take IRT relation. And I can be written as, that is equal to E, same battery under EMF, E small r plus R1 whole square is the current due to first cell, R1 into T is equal to, for second resistance R2, same cell, same source, so EMF is same and internal resistance also same, but resistance is different. So I2 is equal to E by small r plus R2 whole square into R2 into T. Small t cancel both sides, E square also cancel both sides. So that implies R1 divided by small r plus R1 whole square is equal to R2 divided by small r plus R2 whole square. That implies by cross multiplication R1 into small r plus R2 whole square is equal to R2 into small r plus R1 whole square. So A plus B whole square expansion, R into small r square plus 2 small r R2 plus R2 square, A square plus 2AB plus B square formula. That is equal to R2 into R square plus 2R R1 plus R1 square. That implies this is R1. R1 into small r square plus 2 small r R1 R2 plus R1 R2 square is equal to R2 small r square plus 2 small r R1 R2 plus R2 R1 square. Both sides 2 small r R1 R2 cancel, and R1 small r square minus R2 small r square is equal to R2 R1 square minus R1 R2 square. So that implies small r square is taken as common on left side. So remaining term R1 minus R2. Here R1 R2 we can take it as common. So R1 minus R2 remaining. Both sides R1 minus R2 cancel. So that internal resistance small r is equal to square root of R1 R2 is our answer. That is option 3. Next question. Question number 52, page number 107. Find the value of capital R so that no deflection is noticed in the galvanometer when the switch S is closed or open. First draw the circuit diagram which is given in the question. Yes, this is the given circuit, and here also 2 ohms, then galvanometer, and then switch. Values are here 3 ohms and it is 1 ohm. Here also 1 ohm. This is 2 ohms, 3 ohms, and here also this is 3 ohms, and it is given capital R, and it is 8 ohms. The question is, find the value of capital R so that no deflection is noticed in the galvanometer when the switch S is closed or open. S is closed or open, no current is passing through galvanometer. It means it is clearly mentioned in the question, Ig is equal to 0. Current passing through galvanometer, either the switch S is closed or open, no deflection in the galvanometer, means Ig is equal to 0. So Ig is equal to 0 andre, it is also a Wheatstone bridge, but Ig 0 andre, it is a balanced Wheatstone bridge. Balanced Wheatstone bridge. So now the given circuit can be redrawn for convenience. For convenience, let us draw the given circuit between A and C. Between A and C, 3 ohms. So this is A, this is B, and C, D. C and B, between C and B, so 2 1 ohm resistors are there in series. Between C and B, 2 1 ohm resistors. So together it is 2 ohms. Between A and D, so 2 3 ohms resistors. 2 3 ohms resistors are there, 3 ohms. So together it is 6 ohm. And between D and B, one resistor R, and in parallel to this R, 8 ohms resistance is also connected. And between C and D, it is 2 ohms, then galvanometer, then switch are connected. So it is yes. It is 2 ohms between C and D. Now between A and B, a battery. Between A and B, a battery was connected, 9 volts and 1 ohm resistance. It is a balanced Wheatstone bridge because Ig is given 0 in the question. So for the balanced Wheatstone bridge, balancing condition of a Wheatstone bridge is equal to P by Q is equal to R by S. What is there in the place of P? 3 ohms. So that implies 3 ohms. In the place of Q, Q, so it is P and this is Q, and here it is R and it is S. 3 by 2 is equal to R 6 by, in the place of S, 8 and R are in parallel. 8 and R are in parallel. So here 3 2 is 6, that implies 2 2 is 4, cross multiplication. 8 R by 8 plus R is equal to 4. 4 1s are 4 2s. That implies 2R is equal to 8 plus R. 2R is equal to 8 plus R. Or 2R minus R is equal to 8. So R is equal to 8 ohms is the answer. That is option 2. Option 2 is the answer for question number 52. Next, question number 53. A potentiometer of 1 meter length, an unknown EMF voltage source is balanced at 60 centimeters length of potentiometer wire, while a 3 volt battery is balanced at 45 centimeters length. Then the EMF of the unknown voltage source is. Here it is a comparison, two cells, one is unknown EMF, another one is known EMF. Question number 53. Question number 53, from E1 divided by E2 is equal to L1 divided by L2. E1 is equal to E2 into L1 divided by L2. That implies E1 unknown EMF, E1 is equal to known EMF is 3 into L1 60, L2 is 45. So 3 1 ja, 3 15 ja, 15 4 ja, that is equal to 4 volts. 4 volts is the answer, option 1. Option 1. Next, question number 54. A potentiometer having the potential gradient of 2 millivolt per centimeter is used to measure the difference of potential across a resistance of 10 ohm. If a length of 50 centimeters of the potentiometer wire is required to get the null point, the current passing through the 10 ohms resistor is. See here, we know that according to the working principle of potentiometer, potential drop across a given length of a wire is directly proportional to its length, that is balancing length, or V is equal to some proportionality constant. That proportionality constant is called potential gradient. So V can be written as IR according to Ohm's law. Potential gradient is given 2 millivolt per centimeter, 2 millivolt per centimeter into L is given balancing length 50 centimeters. So that is equal to 2 into 10 power minus 1 into 5 into 10 power minus 1. 2 5s are 10, 10 power minus 1 cancel. So that is 1 by 10. IR is equal to 1 by 10, or I is equal to 1 by 10 R. R also given as 10. So that is equal to 1 divided by 100. If it is multiplied with 10 by 10, multiplied with 10 by 10, multiplied with 10 divided by 10, then 10 divided by 1000, or 10 milliampere. 10 milliampere, that is option 3. Option 3 is the right option. And next, 55. Read the question, page number 108. Page number 108, starter level, page number 108. The circuit shown here is used to compare the EMF of two cells E1 and E2. E1 is greater than E2. The null point is at C when the galvanometer is connected to E1. When the galvanometer is connected to E2, the null point will be. So here circuit diagram, potentiometer circuit diagram is also given, but circuit diagram is not required to draw here. From E1 divided by E2 is equal to L1 divided by L2. If E1 is greater than E2, then L1 is greater than L2. So L1 length is up to C. L1 from the end A to C. Then L2 is less than L1. L2 is less than L1 andre. It means the point is shifted. That is balancing point. Balancing point is shifted towards left. Shifted towards left of C. Left of C is the answer. To the left of C andre option 3. Option 3 is the right answer. Next, 56th question. In a meter bridge experiment, resistances are connected as shown in figure. The balancing length L1 is 55 centimeters. Now, an unknown resistance X is connected in series with P is equal to 3 ohms, and the new balancing length is found to be 75 centimeters. The value of X is, see students, in 56th question, meter bridge question, it is P by Q is equal to R by S or L1 divided by 100 minus L1. So, P is given 3. 3 by Q is equal to L1 balancing length is given 55. 55 divided by 100 minus 55 is 45. So, that is 5 11s, 5 9s. So, that implies Q is equal to 27 divided by 11 ohms. Now, along with P, X ohms resistance is connected in series. So, therefore, now P plus X by Q is equal to L2 divided by 100 minus L2. Here L2 is given as 75. So, 75 divided by 100 minus 75 is 25. So, that is equal to 3. Or P is equal to 3. 3 plus X divided by Q is equal to 27 by 11 is equal to 3. By cross multiplication, 3 plus X is equal to 3 plus X is equal to 3 into 27 divided by 11. That implies, so 3 7s are 21, 3 2s are 6, 8, 81 by 11, or X is equal to 81 by 11 minus 3, that is equal to 81 minus 33 divided by 11. So, that our answer is 11 minus 3, 8, 7 minus 3, 4, 48 by 11 ohms. 48 divided by 11 ohms, that is option 3. Option 3 is the right answer. Next, 57. Question number 57. In the circuit shown in figure with steady current, the potential drop across the capacitor must be. See, first you draw the circuit diagram. So, V volts cell and R capital R resistance, and in the second line also V volts, and then here capacitor. Capacitor is connected here. Capacitor of capacity is C along with the SL of voltage V, and here 2V it is, then 2R. This circuit is given in the question. And what is the question? Read once again. In the circuit shown in figure with steady current, the potential drop across the capacitor must be. Potential drop across the capacitor. So, here under steady state, steady state is nothing but until the capacitor is charged fully, current flows through the capacitor. Once the capacitor is charged fully, no current is passed through capacitor. That state is called steady state. So, under steady state or at the steady state, once the capacitor is fully charged, no current flows. No current flows through capacitor. So, therefore, the circuit can take without capacitor, because when no current is passed through that middle portion, so it becomes ineffective. Middle line becomes ineffective once the capacitor is fully charged. So, only upper line and bottom line will only remains. So, it is 2R. Therefore, in this case, now according to KVL, according to KVL. So here let us assume that from 2 volts to 1 volt battery, let us imagine that current I flows in the circuit. So according to KVL, so here 2V minus 2IR minus IR minus V is equal to 0 according to KVL, Kirchhoff's voltage law. According to Kirchhoff's voltage law. So 2V minus V minus 3IR is equal to 0, or V is equal to 3IR, or I is equal to V divided by 3R. I is equal to V by 3R. Now let us take the names here A, B, C, D, E and F. So now KVL is applied. KVL is applied for F, C, D, E, F, upper portion of the circuit. According to KVL, V plus Q by C. So Q divided by C, potential difference across. So as for the current direction, here you can take it as like this. So it is minus, not plus, as per the sign convention. As per the sign convention, let us take here towards plus only. Towards positive plate, so therefore plus only. V plus Q by C minus IR minus V is equal to 0. So here minus V plus V cancel, that implies Q by C is equal to IR. Q by C is nothing but potential drop across capacitor. That is our answer. Potential difference across capacitor. Potential difference across capacitor. So Q by C is equal to, what is I here? V divided by 3R into R. So RR cancel. So that our answer is V divided by 3. Potential drop across capacitor is V by 3. That is option 4. Option 4 is the right answer. And next, last question. It is question number 58. Read the question. In the given circuit diagram, the current through the battery and the charge on the capacitor respectively in steady state are. Here also steady state is given. Under steady state or at steady state. So first we should draw the circuit diagram which is given in the question. So this is the circuit diagram given in the question. Here 6 volts battery, resistances continuously 1 ohm, 2 ohm, 3 ohm and 4 ohm, and capacity 0.5 microfarad capacity. Same under steady state, last line, that is capacitor line, becomes ineffective. Once the capacitor is fully charged, no current is passed through capacitor. So therefore, except that last line, remaining 3, that is 1 by 1 plus 1 by 2 plus 1 by 3. So LCM is 6, 6 plus 3 plus 2, that is equal to 11 by 6, or RP is equal to 6 divided by 11 ohms. RP is equal to 6 by 11 ohms. So therefore, current according to Ohm's law, I is equal to V by RP. V is equal to 6, RP is equal to 6 by 11. 6 cancel. So 11 amperes is the current passing through the circuit. And therefore, and charge on capacitor Q is equal to CV. C is 0.5 into 10 power minus 6 into V is 6. 0.5 is nothing but 1 by 2. So therefore 3 into 10 power minus 6 or 3 microfarads, 3 microcoulombs. 3 microcoulombs is the answer. So 11 amperes, 3 microcoulombs. 11 amperes and 3 microcoulombs. That is option 1. Option 1 is the right answer. Okay, students. So these are the questions given in our material in starter level. Thank you.